Today we're going to talk about sequences. A sequence can be thought of as a list of numbers written in a definite order, a sub 1, a sub 2, a sub 3, and so on. The number a sub 1 is called the first term, a sub 2 is the second term, and in general, a sub n is the nth term. We will deal exclusively with infinite sequences, and so each term, a sub n, will have a successor, a sub n plus 1. Notice that for every positive integer n, there is a corresponding number a sub n, and so a sequence can be defined as a function whose domain is the set of positive integers. A sequence is a function where the domain is a set of consecutive positive integers beginning with 1. An infinite sequence is a function having for its domain the set of positive integers from 1, 2, 3, 4, and continues going. A finite sequence is a function having for its domain a set of positive integers from 1, 2, 3, and continues till some number n. Now there are formulas for sequences. We typically write them as a sub n. So we'll write a formula and denote it as a sub n. In a formula, the function's values are known as the terms of the sequence. The first term in a sequence is denoted as a sub 1, the fifth term a sub 5, and the nth term, or the general term, is a sub n. But we usually write a sub n instead of the function notation f of n for the value of the function at the number n. The notation can be in sequence form when you list out the numbers, but can also be denoted in brackets a sub n, or in brackets telling you it's starting with the number 1 and going towards infinity. Now when you're listing the numbers, as in a sub 1, a sub 2, etc., these would be listing the actual terms of the sequence. Whereas this a sub n, or this a sub n with the 1 and infinity notation, those are actually denoting the formula. So let's look at an example. Example 1 states, some sequences can be defined by giving a formula for the nth term. If the following, or in the following examples, we give 3 descriptions of the sequence. One, by using the preceding notation, another by using the defining formula, and a third by writing out the terms of the sequence. Notice that n doesn't always have to start at 1, but typically in this class, for the most part, we'll be starting with 1. So let's look at A, B, C, and D. Here we have 1 notation. This is telling us n over n plus 1 from 1 to infinity for our n values. This is the formula, n over n sub 1 denoted as a sub n. And now we could put it in terms of a list. So since we're starting with 1 and going towards infinity, our list would be written with brackets. And we would need to plug a 1 in for our n's, since that's our first n value. So we would end up with 1 over 1 plus 1, which would be 2. So this would be our first term. This is when n is equal to 1. Our second term would be when n is equal to 2. So this would be when we have 2 over 2 plus 1, which would be 3. Our third term would be when n is equal to 3. So we would end up with 3 over 3 plus 1, which would be 4. And since this sequence goes towards infinity for our n, we can just do a comma, dot, dot, dot to show that this pattern continues on. So that's how you can write it when you're writing out each of the terms. Let's try B, C, and D. In B, we have a negative 1 to the n times n plus 1 over 3 to the n power. This negative 1 to the n is going to alternate the signs of your sequence. So it will make some terms negative and some terms positive. This n plus 1 will affect the numerator's value, and the 3 to the n in the denominator is going to make our denominator a multiple of 3. So here's our formula. So what we're going to do is the same thing we did before, which is simply to write a bracket and write out a few terms of the sequence. Let's start with the first term. So that's when n is equal to 1. So when n is equal to 1, we'd have negative 1 to the n power, which n is 1, so negative 1 to the first power, which means that our numerator is going to be negative. Then we would have 1 plus 1, which would mean we'd have a 2. So our numerator is going to be negative 2 over, and then our denominator is 3 to the first power, so 3 to the first power is 3. So our first term is negative 2/3. Now let's find our next term. Now we have n to the second. So for that negative 1 to the nth power, we're going to have an exponent of a 2. So negative 1 to the second power would make this a positive 1. So we're going to have a positive second value. If you want, you can put a positive there just to show that you've taken care of that. You don't have to. Typically, you won't see that, but just for this, we can start writing it that way. Then we're going to have our n value of 2. So 2 plus 1 would be a numerator of positive 3 over, and then our denominator would be 3 to the second power, which would be 9. If you wanted to, you could take away that plus sign, since not having it there is just fine. Now we can do our third term, n equals 3. So when n is equal to 3, we would have an odd exponent for our negative 1, so we would result in a negative numerator value. 3 plus 1 would give us 4, so our numerator is going to be negative 4. And then 3 to the third power in the denominator would give us 27. Oh, I forgot my ... dots. Since this goes from 1 to infinity, we can put our bracket after 3 dots to show that it's continuing on. Okay, so what I'd like you to do is to take a moment and to try to do number 3. Now this is telling us our first value is not starting at 1. This is telling us that our first value is starting at 3. So our n equals whatever our first term is going to be 3. So our first term is n equals 3 in this one. So take a moment and see if you can determine what it would be at n equals 3, n equals 4, and n equals 5. Okay, so hopefully you were able to determine that your first term of your sequence would be 0, second term would be 1, third term would be square root of 2, and then you can put comma ... since it's continuing on. Notice that I've been writing n equals 3, n equals 4, n equals 5, and in the ones above, n equals 1, and so forth underneath each of the terms. That's not necessary. You do not have to write this n equals 3, n equals 4 notation underneath. All you truly need when you're writing out the sequence list is just your bracket, your values, and your ending bracket. Okay, so take a moment and try and see if you can determine what D would be. Now notice, before you begin, just like C was slightly different, it didn't start at 1 like the default ones are, this one is actually starting at n equals 0. So your first term is not going to be n equals 1, it's not going to be n equals 3, it's going to be n equals 0. So see if you can determine what this would be. Okay, so hopefully you can see that your n equals 0 term would be 1. The reason for that, if you want to take a closer look, would be because when you plug a 0 in for n, you would end up with the cosine of 0 times pi over 6, which is really just the cosine of 0, and the cosine of 0 is 1. For the second one, you would really end up with the cosine of 1 pi over 6, or pi over 6, and that answer is the square root of 3 over 2. And then for the next one, you would end up with the cosine of 2 pi over 6, and really that's just the cosine at pi over 3 if you reduce it, so that's 1/2. So you would definitely need to rely on some unit circle knowledge for this to help answer this question, and you could write as many values in the sequence as needed. Now, there are special kinds of sequences. One of them is called arithmetic sequences, and this is when you're dealing with repeated addition or subtraction. So a sequence in which the first term, or excuse me, the sequence in which each term after the first term is found by adding the same number to the preceding term is called an arithmetic sequence. A sequence is arithmetic if there exists a number d called the common difference, such that to get to your next value, a sub n plus 1, you take the prior value and add that common difference for any integer n greater than or equal to 1. So is there a rule for finding the nth term of the arithmetic sequence? In other words, is there a formula for this? And the answer is yes. So this is basically asking, is there a formula for a sub n when a sub n is arithmetic? So to answer that, to find the formula for the general nth term of any arithmetic sequence, we can denote the common difference by d and write out the first few terms to look for a pattern. After you find that pattern, the nth term of the arithmetic sequence is given by this formula. A sub n equals a sub 1, which is the leading term, the first term in your sequence, plus the product of n minus 1 times your common difference. Now remember, the common difference is the amount that you're adding or subtracting to get to the next term. So this is the general formula for the arithmetic sequence. Now, for example 2, for each of the following arithmetic sequences, we need to identify the first term, so that a sub 1. We need to identify the common difference, which is our d, and we need to find the rule for the nth term. When they're asking for the rule, they're asking for the a sub n formula for the arithmetic sequence. So let's look at A. A says 6, 10, 14, 18, and 22 are the first several terms of this sequence. So in this, we could say, for example, the first term is 6, the second term is 10, and the third term is 14, and so forth. To get from 6 to 10, what did we do? We added 4. To get from 10 to 14, what did we do? We added 4, and you can probably start to see that for each of these, they're adding 4. So to start with our first task, we need to identify the leading terms. That's our a sub 1. So our leading term, according to our notes up here, is 6. We also need to determine what our common difference is. So our common difference is what we added or subtracted to each of these. So that's going to be a positive 4. So our d value is going to be 4. Now we need to plug it into this formula. Now remember, it's a sub n for the name of our formula. Then we have to put our leading term, which again, it starts with a sub 1, which we've identified as 6, so we'll put a 6 down, plus the quantity n minus 1 times the common difference. Now the common difference that we found is 4, so this is going to be multiplying with 4. Now the best thing to do is to try to simplify this as much as you can. So we are going to take the 4 and distribute it through this set of parentheses here. So this is going to end up with 6 plus 4n minus 4. And then as you can see, we have some like terms that we can add together. So we would end up with 4n plus 2. And this would be our general formula for this specific arithmetic sequence in example A. Let's look at example B. So example B is going to be very similar. Again, you can look at the first several terms. So our first term here is n sub 1, a to the n sub 2, and so you can see each of the terms of the sequence. It looks like they have 5 items listed for us. And we can also look to see what we're doing to get to the next term. So in this case, it looks like we're actually subtracting 6. 0 to negative 6 would need to be subtracting 6. From negative 6 to negative 12, it looks like we're subtracting 6. From negative 12 to negative 18, it looks like we're subtracting 6. So we already have identified, we just need to write down our first term, which is a sub 1, which in this case is 0, and our common difference, which we've determined is negative 6. Now we're going to put it into the formula, a sub n. Remember, you start with your leading term or your first term, which we've identified as 0, plus the quantity n minus 1 times the common difference. Remember, that's our d value from the formula, and our d value is negative 6. Again, we need to take a moment and try to simplify this. So we're going to take that negative 6 and distribute it through. We also don't need to really write a 0 because it's not truly doing anything for us. So we're going to have negative 6 times n, and then negative 6 times negative 1, which would be positive 6. So it looks as if our formula for this one is already simplified, and our formula is negative 6 times n plus 6. Now for our last example, we can note our first few terms. So n equals 1, n equals 2, and n equals 3. So our first term looks like it's 1/3, our second term looks like it's 2/3, and our third term looks like it's 1. Now we can also try to determine what our common difference is. So what did I do to get from 1/3 to 2/3? It looks like I added 1/3. And to get from 2/3 to 1, it looks like I've also added 1/3. To get from 1 to 4/3, it looks like I've also added 1/3. So it looks like our common difference is 1/3. So let's go ahead and write those items down. So our first term, a sub 1, is 1/3. And our common difference, our d value, is also 1/3. Now we're going to put it into our formula, a sub n. Remember, you start with your leading term. In this case, that's 1/3, our a sub 1, plus the quantity n minus 1, which is multiplying with our difference here, which is a positive 1/3 since we were adding. Then what we're going to do is take that 1/3 and distribute it through. And so we would end up with a positive 1/3 plus 1/3 n minus 1/3. Then we can combine some like terms since we have two constants there that can combine together. So it looks as if our formula is simply going to be 1/3 times n, since positive 1/3 and negative 1/3 would cancel. So 1/3 times n is going to be our formula for this last example. Now, there are other types of sequences. The next type that we're going to look at is something called a geometric sequence. A geometric sequence is repeated multiplication. So we're going to see what we're multiplying by. So a sequence in which each term after the first term is found by multiplying the preceding term by the same number is a geometric sequence. The number that is multiplied by each term to produce the next term is called the common ratio. A sequence is geometric if there is a number r called the common ratio such that the division of the next term in the sequence by the prior term in the sequence gives you the r value. Or in other words, if you want to get to the next term in the sequence, you take the term you currently have and multiply it by r for any integer n is greater than 0. So, to find the nth term of a geometric sequence, so again, this is just the formula for your a sub n if we're dealing with a geometric sequence, is to find the formula for the general or nth term of any geometric sequence. We denote the common ratio by r, write out the first few terms, and look for the pattern. Once you find the pattern, the nth term of a geometric sequence is given by the formula a sub n equals the first term in your sequence times the common ratio, the r value, to the n minus 1 power for any integer n greater than or equal to 0. So let's look at example 3. And for this, we're going to need to use this geometric formula. So for each of the following geometric sequences, we need to identify the common ratio and find the rule for the nth term. Again, that rule is going to be our geometric formula. I would also suggest determining what your first term is. So let's look at A. If we start with all of the terms that we have here, it looks as if our first term when n is equal to 1 is 4. Our second term when n is equal to 2 is 16, and our third term when n is equal to 3 is 64, and so on. So it looks to me like our first term, a sub 1, is 4. Now, how did we get from one term to the next? How did we get from 4 to 16? It looks like we multiplied by positive 4. How did we get from 16 to 64? Again, it looks like we multiplied by 4. How did we get from 64 to 256? So it looks as if our common ratio, r, is a positive 4. So now that we know those two crucial pieces of information, we can write the geometric formula. So that is a sub n is equal to the first term in the sequence, which in this case is a 4, times the r value. So again, we're just using this formula up here. So our r value we found to also be 4. And then we have the n minus 1 as our exponent. Now, believe it or not, this can be simplified, and we're going to have to use some rules of simplifying exponents. When you have an exponent of n minus 1, that means you have a 4 to the n multiplying with a 4 to the negative 1 power. When you have multiplication of like bases, remember you can add the exponents together, which would result with what we have here. So what we're going to do is undo this addition of our like bases here for the powers, and we're going to break up this exponent. So we are going to write that as 4 times 4 to the n times 4 to the negative first power. Now, when you have multiplication of like bases, in this case 4 to the first power and 4 to the negative first power, when you have multiplication of like bases, we know that we add their exponents. So we're actually going to add those exponents together, and that will result in 4 to the 0th power times 4 to the n. And it's 4 to the 0th because 1 plus negative 1 is 0. Now we know that anything to the 0th power is really just 1. So what we're left with is really just 4 to the n power, and that is going to be our simplified geometric sequence for example A. Let's see if we can do something similar with example B. So once again, we need to look and see what our terms are. So here's our first term, our second term, and our third term. So I'm going to go ahead and take note that my first term is 1. I also need to determine what my common ratio is. So how did I get from 1 to the next? So to get from 1 to negative 2/3, it looks like I may have multiplied by negative 2/3. To get from negative 2/3 to positive 4/9, I did also multiply by negative 2/3. So it looks like our common ratio here is a negative 2/3. So now that we have those two crucial pieces of information, we can go ahead and write down our formula using the description above. A sub n is equal to our first term times our common ratio to the n minus 1 power. So our first term is 1 times our common ratio And I'm going to put that in parentheses since it has a negative there. So negative 2/3 to the n minus 1 power. Using a very similar or the exact same idea that we did before, we're going to break up that exponent into multiple pieces. So I really don't need the 1 anymore. So I'm just going to write negative 2/3 to the n times negative 2/3 to the negative 1 power. Now, I can simplify this. I didn't need to bring the 1 down because it's just a 1, so I didn't do that, but I can simplify this piece here to the negative 1 power. I know it doesn't combine with anything like in the prior example. However, anything to the negative power, you can distribute that negative 1 to both the numerator and the denominator, and then they would change places, and your denominator would become your numerator and your numerator would become your denominator. So just kind of going through our exponent powers from your algebra days and your exponent rules. So we're still going to have the negative 2/3 to the n, but this is going to flip. So now we're going to have a 3 over negative 2. And they're still to the first power, but we don't need to write that. And then, of course, this can simplify. So I would probably put this in front since it seems as if it's a coefficient. So I'm going to write my final answer as negative 3/2 times negative 2/3 to the nth power. And that would be my simplified geometric formula for example B. Now example 4 is going to be slightly different. When we look at this, if we were to try to write a formula for this, to start, if I try to look at the first term here, n equals 1, and compare it to my next term, n equals 2, and my next term, n equals 3, and so forth, you can kind of see that there is no common difference nor a common ratio that would work for this sequence. So what that's telling us is that we do not have an arithmetic sequence, and we do not, if I can spell apparently, have a geometric sequence. So when you don't have one of those very prescribed sequences, the next best thing is to look for patterns. Okay, so that is what we're going to do. To start, I would suggest kind of looking at your numerator to see what's happening up there. So in my numerator, I can see that they are actually perfect squares. So my first term has a numerator of a 1, so that's 1 squared. My second term has a numerator of a 4, and that's 2 squared. My third has a numerator of a 9, and that's 3 squared. So it certainly looks to me like what we have here is our n value, right? Because it matches up with our n equals 1, n equals 2, n equals 3. So the first term squared, the second term squared, third term squared. So it looks like our n is being squared in the numerator. In the denominator, remember you're starting with your n equals 1, it looks like I'm 1 more than n equals 1. So I have a denominator of a 2. And then in my second term, I have a denominator of a 3, which is 1 more than the n value. So n equals 2 plus 1 would give me the 3. And it looks like in the third term, it's also 1 more than my n value. So my n is 3 plus 1 would give me that 4. So it looks to me like our denominator is going to be n plus 1. But there is something that we're missing in this. We have alternating signs. So our first term is positive, our second term is negative, our third term is positive, our fourth term is negative. So there is a way to work with that. And whenever you see something that's alternating sign, you have two choices. Either -1 to the n, which we've actually seen before in a prior example, or -1 to the n plus 1. So if you're dealing with -1 to the n, that means that anything from your first term, so all of your odd terms, so n equals 1, n equals 3, n equals 5, are going to be negative. Okay, so this would be our odd terms are negative. And when you have -1, n plus 1, this would actually make your odd terms positive. Okay, so that would mean, in other words, your first term. And many times you just kind of look at your first term to determine it. So your first term is positive. Okay, so what is that telling us? That means that for this example, putting all of this together, my formula, a sub n is going to equal my numerator, which is n squared, over my denominator, which we determined to be n plus 1, and then we need to determine which sign choice we're going to have. And because my first term is positive here, I'm going to use the -1 n plus 1. So I'm just going to put that right in front, -1 n plus 1, and put a multiplication sign between those. So this is the first pattern type that you're going to have to work with, and you just kind of need to break it apart as best you can, looking for if they have alternating signs and any sort of pattern in the numerator and denominator to help you break it down. The next section of the notes is going to talk about limits of sequences. So this is where the calculus stuff is going to come in. I'm sure you thought the first part wasn't so bad, but now we're going to get into the calculus. But it's not so bad here either. So here it says a sequence such as a sub n equals n over n plus 1 can be pictured by plotting its graph. So this is the graph of that function. It says, note that since a sequence is a function whose domain is the set of positive integers, and again, that's a really important thing to think about, the domain of these functions is only going to be positive integers, right? So that means its graph is going to consist of isolated points. And the coordinates are going to be right here. Okay, so they are going to be 1 for your n value, and then a sub n. So they're going to be of this form, where n is the n value that you're working with, and a sub n is the evaluation of your sequence at that n value. So let's look at this graph to kind of see what I mean here. So here we see all these points kind of plotted. This first point here, that has an n value. Notice my horizontal axis is n. That has an n value of 1, so that point is 1, comma. And notice my y axis, or really my vertical axis here, is a sub n. So that means this point is 1, a sub 1. And the second point would be 2, a sub 2, and so forth. So each of the points is obtained from evaluating your sequence at each of the n values. Okay? So it appears that the terms of this particular sequence, a sub n equals n over n plus 1, are approaching 1 as n becomes large. So you can kind of see that here. It's starting out at 1, almost halfway, and then we have it kind of approaching this horizontal blue line here at the value 1. So it looks like the limit of the sequence is approaching 1 as our n values get larger and larger and larger. And so we would indicate this by writing the limit as n approaches infinity of our sequence, which in this case is n over n plus 1 equals 1. In general, the notation is the limit as n approaches infinity of a sub n equals L, means that the terms of the sequence a sub n, so that's the name of our sequence here and inside our limit notation, approach the limit L as your n's become really, really big. Now, before we go any further in limits of sequences and doing more rigorous problems with those, I do want to show you how to graph a sequence on your calculator. So you might want to get your calculator out, and we need to put this in parametric form. So what does that mean? Remember, you can change the mode of your calculator. So turn your calculator on and go to mode. And for this, our mode is going to be parametric. So we're going to come down to the function parametric or polar, and we're going to choose parametric and select that by hitting enter. And then we're also going to, instead of having a connected graph, we're going to change it to plotting just dots. So make sure those two items are selected. Okay, so now we're going to go to our y equals, and we have to put this in parametric. Okay, so to do that, we're going to have our x sub 1 be just the variable t, and then our y sub 1 is going to be the function that we're working with. So the function that we were working with, if you recall, was n over n plus 1, and in our calculator it's just going to be t over t plus 1. So variable t over parentheses t plus 1. So there we have that. Then we need to make sure that our window is going to be appropriate. So let's just look at our window and make sure. By default, it's kind of all those pi's and 2 pi's and things. So let's change this up a bit. So first of all, for your t min and t max, it would make sense to start with t min of 1, since that's our n value in this case. So we typically start with an n value of 1. And maybe I want to show just like the first 10. So I'll just do 1 to 10 just to kind of get an idea of what's happening. Your t step, since we're only plotting at positive integers, this should be a positive 1. So we'd be starting at 1, and since our t step is 1, that would mean our next value would be 2, 3, and 4 all the way to 10. Now for our x min, just kind of think about the type of x values we would have. We're not going to have anything less than 0, so we're going to go from 0 to 10. And then our scale, of course, can be 1. And then for our y values, that's going to be, what type of values are we going to have here? Now, we already discussed that the limit of this particular example is going to be 1. So I might want to have this go from 0 to 2, just to kind of show a little bit of space beyond the graph. So if I go ahead and hit graph, we can see that now we have our sequence graph, just like we do over here. In the notes, each of those points is plotted at a positive integer, and there is how you graph a sequence. So now let's continue on with the idea of a limit of a sequence, since we now can, graph things on the calculator and have an idea that a sequence can in fact have a limit. So a sequence a sub n has a limit L, and we can write it in 2 ways. One is the limit as n approaches infinity of a sub n equals L, or a sub n approaches L as n approaches infinity. And basically what this is saying is that as you're getting very large n values, your sequence is approaching a particular number, and that number is L. So if a limit exists, we say that it converges. There are times when this will not happen, and that is when we say it diverges. And this is when your limit would approach either infinity or negative infinity. Again, just kind of think of it as the only major difference between a sequence's limit and a function's limit is that the n value that you have has to be an integer. Okay, so here we have three graphs. We're going to focus on this first one here and then this bottom one. So this graph is obviously the graph of a sequence, right? And it looks to be approaching this value L. This graph on the bottom looks like it's the function that's derived from this sequence because it's kind of following that same path, right? But this is a function. Notice it has values not only at integers but also in between. the integers, and it also has the same limit. So as you can see, basically, if the function f of x that's derived from your sequence has a limit, so obviously we see this one down here does have a limit, then the sequence itself, the one up here, will also have a limit, and those limits will be the same. However, the converse for that is not always true. Just because a sequence has a limit, the function that's derived from it does not always have to have a limit. And that's mainly because of that idea of the n value being only integers. Okay, so something to remember is that when you have the limit as x approaches infinity of 1 over x to the r, the limit of that is equal to 0. And that was a really big idea, particularly when you were in Calc 1, but also when we were talking about L'Hopital's rule earlier. Anything that had the denominator get really, really large and your numerator stay constant, your limit became 0. Well, that idea is going to apply to the limits for sequences as well. As our n value approaches 0, so n to the r power, as that's getting really large in the denominator and your numerator is staying constant, your limit for that case will also equal 0. And what we'll see is that many of the laws that you had for just general limits can also hold for sequences, and their proofs are similar. And so those laws are written over here to the right. So if we had two sequences, a sub n and b sub n, and they are convergent sequences, and c is a constant, then these laws that we have that should look really familiar to the prior limit laws that you knew, these will still hold. So, basically the addition of them, you can split them up. The subtraction of them, you can split them up. If you have a coefficient, you can bring it forward. The multiplication of them, you can split them up. The division of them, so like your product rule was the multiplication, this is the quotient of them. As long as your limit in the denominator doesn't equal 0, you can split up the limit of the numerator and the limit of the denominator. And then, of course, if you have your power here, your sequence to a power, you can take the limit of the inside and then take the power once you find that limit. So these limit laws are actually quite convenient, and we'll see them put into use in later questions. There's also a couple of other theorems that you may have come across in prior calculus classes. So the first one is the squeeze theorem, and this can be adapted for sequences as follows. So basically the squeeze theorem says that if you have three sequences, sequence A, sequence B, and sequence C, sequence A is below sequence B, which both of these are below sequence C. So in other words, B is between sequence A and sequence C. So what I'm talking about are the values, right? So the values of our A are less than the values of our B, which are less than the values of our C. So all of these are kind of sandwiched together, like one of them is the top piece of bread, the other one is the bottom piece of bread, and B would be in the middle. So that'd be all your meat and cheese, right? So it's sandwiched between them. And what this is saying is that if you know the limit of the bottom sequence, A, and you know the limit of your top sequence, C, and those two happen to have the same limits, then B, the middle sequence, would also have to have the same limit because it's sandwiched between two that already have the same limit. And so this picture here is kind of showing that to us. Here we have a bottom sequence, that's our A, that's our bottom loaf of bread, right? Here we have our top sequence, sequence C, that's our top loaf of bread, and B is sandwiched between them. Notice that A and C are both converging to the same limit value. That means B also would have to converge to the same limit value. And then finally, another useful facts about limits of sequences is that if you have the absolute value of a limit as n approaches as n approaches infinity equaling 0, then the limit without the absolute value would also equal 0. So what we're going to do is do several examples to try and finish this out. We're going to do several of these and then practice some of the ideas that we've just talked about. So this first one here says we need to find the limit as n approaches infinity of n over n plus 1. And this one should look familiar because we've actually talked about this one before. We saw the graph of it in our notes. So you may have an idea that this one does in fact converge, but let's see what would actually happen. So if I were to just try to evaluate this, I would end up with infinity over infinity because my n value is getting large. So n is going towards infinity. So the numerator would be infinity, and then n plus 1 would also be infinity. So this should be screaming to you to apply L'Hopital's rule because that is infinity over infinity. So if I do that and apply L'Hopital's rule, and take the derivative of the numerator, remember, separately from the derivative of the denominator. Just because this is a quotient does not mean we're using the quotient rule for L'Hopital's rule. So the derivative of my numerator is 1, and the derivative of my denominator is 1, and then apply the limit as n approaches infinity. That would, of course, be 1. So we would know that this converges to 1. Now, you could have also gone back to some of your pre-calc and early calc rules when you were talking about the limit, and this only applies when n is approaching infinity, but looking at the powers of your largest term. So in this case, my largest term in my numerator is just n, so that'd be to the first power, and the degree of the largest term in my denominator would also be 1 because this is n to the first power. So because they are equal, you're just going to look to see what's happening with them, and you take, when they're equal, the ratio of the coefficients, right? So you're just going to just recognize that you have n over n, and that would basically cancel out to a 1 because your ratio is 1 over 1, which of course equals a converging limit of 1. Now, you can also, if you don't remember those rules, you can also kind of go back to your calculus ideas and you divide by the largest term in your denominator. So you would take n and in the numerator and n plus 1 in the denominator. Now my largest term is n, and so you're going to divide by n in both the numerator and the denominator, and that would simplify to be the limit as n approaches infinity, and the numerator would become 1, right, because n divided by n is 1, and the denominator would become, well, n divided by n is 1, plus 1 divided by n would be 1 over n. Now, this term here would approach 0, because anything with a growing denominator and a constant numerator, we talked about that a moment ago, that would be a 0. So we would end up with 1 over 1 plus 0, which would equal 1. So there are many ways that you can kind of get through these questions. You can use the ratio of the coefficient idea as long as you state that that's what you're using. The ratio of the coefficients is 1, therefore it converges to 1, and so forth. You can use L'Hopital, or you could actually go through the whole limit process. Okay, let's look at example 7. Again, this one could be done a few ways. So this one is asking if our sequence is convergent or divergent. So that means we need to take the limit as n is approaching infinity of our sequence here. Okay, and when I do that, I see that I would end up with infinity over infinity. So again, it's screaming L'Hopital's rule to me. So we need to apply L'Hopital's rule by taking the derivative of the numerator and the denominator. So the derivative of the numerator is just 1. The derivative of the denominator is going to be a chain rule. So we're going to have that 1/2 in front from the derivative of the square root. The inside remains the same, to the negative 1/2 power times the derivative of the inside, which would just be 1. This, of course, can be simplified a bit. So we have the square root. So when you're dividing by a fraction, remember you're really multiplying by the reciprocal. So this would be multiplying. So we would end up with a 2. This negative exponent would bump up to our numerator. So we would end up with the square root of 10 plus n in the numerator, and then the 1 in the denominator isn't really necessary to write. And so now if we were to apply our limit, we would see that this is going towards infinity, so we would say that this is diverging. Okay, so this diverges. Another way to think about this one is to use that idea of the ratios of the coefficients. So our numerator is an n, and our denominator is basically the square root of n, if we kind of look at the largest exponent there. So the exponent of our numerator is a 1, the exponent of the denominator is a 1/2, so the numerator is larger, and so that means it's going to grow faster, and so that means it's approaching infinity. When the denominator grows faster, it's approaching 0. When the numerator is growing faster, it's approaching infinity. And when they're equal, like in the example above, you take the ratio of the coefficients. But again, please be mindful, this is only applicable when you have n approaching infinity for these types of questions. Okay, so now let's look at example 9. We need to determine if the sequence -1 to the nth power is convergent or divergent. So what we're being asked is, does the limit as n approaches infinity of -1 to the nth power come to a number, a limit, or does it go to infinity or negative infinity? So because of this -1 to the nth power, I kind of already know that the sign of this is going to be bouncing around, and it's going to go from positive, negative, and so forth. So, and I know because we're dealing with a 1, it's going to be dealing with just a 1 value. So it's basically going to be bouncing around between -1 and 1. So maybe if I tried to apply the absolute value idea, maybe that'll make things a little nicer. And if I tried to do this, I would actually find that the limit does not equal 0. And remember the rule, when you have the absolute value going there, the limit has to equal 0 in order for that particular theorem to apply. And in this case, it wouldn't. And I would know this because if I actually took the limit and did L'Hopital's rule and applied it, I would find that the limit actually is 1. So L'Hopital would make this limit equal to 1. So L'Hopital, when I applied, it would make our limit equal to 1. So in this case, this particular idea won't work. So maybe it's just a good idea to kind of figure out what's happening with this in general. So if I were to start and just write out a couple points in our series, or excuse me, in our sequence, what would happen? So if it's n to the first power, because our n value is 1, I'd get a -1. With an n value of 2, it'd be -1 to the second power, so that'd be +1. N equals 3 would be -1 to the third power, so -1. And I can see that this pattern is just going to continue. So unfortunately, this particular one would not converge, it would diverge, because it's truly going to go between -1 and 1 only. And so it's not going to choose one or the other to kind of hone in on. And so we would say that this is divergent, or that it diverges. Okay, let's look at example 10. Example 10 states that as n is approaching infinity, what's the limit of -1 to the nth over n? And we need to determine if it exists. So this means we are trying to find the limit as n approaches infinity of -1 to the n, and I'm going to write this as 1 over n. 1 over n is the same as dividing by n. So This one I know the first part from above didn't really work with the absolute value, but maybe this part will. So let's see what happens when I try to do the absolute value piece. Now, because of this 1 over n here, because of the limit of that particular piece of it, the 1 over n, as n approaches infinity, so due to that, because of that piece, and n is going to become large with a constant numerator, I know that the limit of that is going to equal 0. 0 times anything is going to give me 0. So 0, even times a -1 or a +1, is going to give me 0. So the absolute value of this limit process is going to give me 0. So now I know that that theorem, the absolute value theorem, does apply. And it's that absolute value theorem, just to remind you, it's that absolute value theorem at the top here. If the limit of the absolute value of the sequence is equal to 0, then the limit as a sequence without the absolute value, just the plain old sequence, it would also be 0. And that's what I'm finding here. I took the absolute value because I thought it might be a little weird with this -1 and 1 thing going on here. So I did the absolute value of it. And because of this 1 over n piece approaching 0, and 0 multiplying either a -1 or a +1 would force this all to go to 0, then that absolute value theorem would apply. And so I can say that as a whole, the limit would converge, and the answer would be 0, right? So it approaches 0, and it would converge. Okay, let's look at number 11. Now with this one, remember the idea of being able to kind of focus on what's happening on the inside here. So first, let's say the limit as n is approaching infinity as the sine of pi over n is our sequence. So sine of pi over n is our sequence, and we're taking it as n approaches infinity. So we kind of already have an idea of what's going to happen here. I know that I have a constant in my numerator here, right? And my denominator is getting large because n is approaching infinity. So I kind of already have the idea that this is really going to be pi over infinity. Whoops, not 8. Over infinity. Got to put it on its side. There we go. I kind of already know that that's going to be equal to 0. So really, I'm just finding the sine. So after applying that idea of the limit, I'm actually really just finding the sine of 0, which of course would be 0. So yes, it converges. But what I want to point out about this one is that you're really focusing on the inside first, right? And so what's happening here is you're really kind of focusing almost on the limit as n approaches infinity of this pi over n. So you're kind of taking a look at what's really changing in this particular sequence. The sine part isn't changing. That's almost like the outside function. The pi over n is what's changing, and that equaled 0. So then we were able to take that idea and apply it to the outside function sine, and then we were just evaluating the sine at 0. So sometimes it helps to focus on the inside part of the function first, and what's really changing in this particular sequence, what's actually being manipulated. All right, example 12. Example 12 states that for what values of r is the sequence r to the nth convergent? And it's telling us that this is a geometric sequence. And we know that because of the r to the nth format here. So what we're going to do is try to determine when is this convergent. And we're just going to try out some things. So what if r is equal to 0? in this particular case, what would this sequence look like? Well, that would mean that r is 0, and that's being taken to the nth power. So when n is equal to 1, we would have, for our first term is 0, because 0 to the first power is 0. When n is equal to 2, it would also equal 0, because 0 to the second power is 0. For the third term, it would equal to 0, and so forth. So when r is equal to 0, we have a limit of 0, right? So it converges, and the limit equals 0. So let's see what's happening with an r value of 1. Okay, well that's 1 to the nth power. Okay, so when n is to the first, that means 1 to the first power, that's 1. When n is 2, our second term, that's 1 to the second power, which is also 1. When n is 3, that's 1 to the third power, which is also 1. So again, you see that we're just kind of staying steady there. So this also converges with a limit of 1. Okay, well, what about when we have an r value of 2? Okay, so 2 to the nth power. What's happening in this situation? Well, when we have our first term, that's when n is equal to 1. So that's 2 to the first power, which is 2. And then we'd have, for our second term, that's when n is equal to 2. So 2 to the second power would be 4. And then our third term would mean n is equal to 3. So 2 to the third power is 8, and so forth. So we can see that this is actually growing. So this is divergent. So it diverges. What about when n is when r is equal to 3? We'll probably end up seeing the same thing. So our first term is going to be 3, and then 3 to the second is 9, and 3 to the third is 27. So we're seeing, again, that diverging idea. Okay, so my bet is if I were to continue going 4, 5, and 6, that would continue to diverge. So maybe if I try some negatives, let's see what's happening there. So if r is equal to a -1, what happens there? So -1 is being taken to the nth power. Okay, so for -1, if I'm dealing with an n value of 1, that's -1 to the first power, which is -1. If I'm dealing with an n value of 2, my second term, that's -1 to the second power, which would be a +1. If I'm dealing with an n value of 3, that's -1 to the third power, that's -1. So I'm starting to see that pattern of that bouncing around between 1 and -1, so I see that this diverges as well. So let's see what's happening at -2, just to make sure we're not crazy. But I bet it's going to diverge. So let's see what happens. So -2. All right, well, -2 to the first power is just -2. -2 to the second power would be +4. -2 to the third power would be -8. So not only is the value changing, but the signs are also changing. So this definitely diverges. Okay. So, okay, well, I'm dealing a lot with whole numbers here. So I've dealt with 1, 2, and 3. I've dealt with some negatives, right? -1 and -2, and I've dealt with 0. So maybe I should look at some fractions, aka decimals, right? So I'll start with maybe a nice one of a half to see what's happening there. So not -1/2, but +1/2. So +1/2 to the nth power. What does that look like? Okay, well, 1/2 to the first power is just 1/2. 1/2 to the second power means 1/4. 1/2 to the third power is 1/8. 1/2 to the fourth power is 1/16. So this is actually becoming a smaller and smaller fraction. So this one actually converges, and it's converging to 0. Okay, so that one converges. That's interesting. What if I have an r value of 1/4? So I'm quickly going to do this. So after writing the 1/4 out, I see that it's 1/4, 1/16, 1/64. So I'm definitely seeing converging again. And it's converging to 0. Well, what about negatives? So what about negative a half? Let's just keep it at that and see what's happening there. So negative a half, let's see what's happening with that. So at negative a half to the first power, I would just have negative a half. Negative a half to the second power would end up being positive 1/4. And negative a half to the third power would be negative 1/8, and then positive 1/16, and so forth. So I know it sounds silly, but although it doesn't seem like it's converging, it actually is. I know that it's bouncing around between the negatives and positives, but the values are actually still getting smaller. So negative a half is coming in to 0 from underneath, and a fourth is coming in to 0 from above, but both of them are still narrowing in on 0. And I'll show you what that looks like with a graph. So here's the graph of it, and I know it's really kind of bizarre to see, but what's happening here is, see how this one's at negative 1/4, and then we have negative 1/8, or positive 1/8 and negative 1/16. Notice how this is further away, and this is closer, and then this is even closer, so you can start to see how it is in fact getting closer and converging to 0. So what does all of this mean? Well, I think it might help to first break this into ideas. So when r is equal to 0, when r is equal to 1, when r is greater than 1, when r is negative, and then we have some fraction ideas. So this is when r is equal to 0. So when r is equal to 0, it converges. When r is equal to 1, it converges. When r is greater than 1, it doesn't work. It doesn't converge. That doesn't help us. When r is less than or equal to -1 here, it diverges. It doesn't work. So this one doesn't help us out. When we're dealing with positive values between 0 and 1. So less than 1 but greater than 0. It works, right? There's some sort of converging happening. And when we're dealing with negative values between 0 and -1, it also works. So in summary, if we look a little further down, kind of putting all of these ideas together, we know that the sequence r to the nth power is convergent if we're dealing with values from -1 to 1, but including 1. So let's go back up and look at that for a minute. So is r between -1 and 1? Yes. Is r equals 1 between -1 and 1, but including 1? Yes. Is r values between 0 and 1 in that range of -1 to 1? Yes. What about from -1 to 0? Yes. So all of the ones that we saw fit into this statement right here. It's convergent if it's between those values. And then what this statement does is tells us that what it's convergent to is either 0 or 1 based on what the r values are. So if r is between -1 and 1, it's convergent to 0. If r is equal to 1, it's convergent to 1. So this theory is going to come into play when we're working on question 15. Okay, last thing we're going to talk about. A sequence A sub n is called increasing if the current part of the sequence is less than the next value of the sequence for all n greater than or equal to 1. That is, a sub 1 is less than a sub 2, which is less than a sub 3. The opposite is true if it's decreasing. So if it's decreasing, that means the current value of the sequence is greater than the next value of the sequence for all n greater than or equal to 1. A sequence is monotonic if it is either all increasing or all decreasing. So let's look at example 14. We're going to show that this particular sequence is decreasing. What does it mean to be decreasing? That means we need to compare the current value of the sequence, which is a sub n, to the next value of the sequence, which is a sub n plus 1. So that would look like n plus 1 in the numerator over n plus 1 quantity squared plus 1 in the denominator. Now, in order for it to be decreasing, that means that the current value, based on our definition, our current value needs to be greater than our next value. So that the current value is larger and the next value is smaller and then the next value is smaller and so forth. So that's what it means to be decreasing. So let's see if that is in fact true. So we are going to have n over n squared plus 1, and we're going to see if this ends up resulting in a true statement. So n plus 1 over n plus 1 squared plus 1. Now we obviously need to try and simplify this as best we can. So we need to try to FOIL out and then combine like terms with this plus 1. So that's going to result in n over n squared plus 1 greater than n plus 1 over n squared plus 2n plus 2. Now, what I'm going to do is I'm going to try to get this out of the fraction here. So I'm going to take this denominator and multiply it through over here. So that'll cancel there, and then I'll take this one, the n squared plus 2n plus 2, and multiply it through. So in other words, I'm kind of cross multiplying. I don't know if you guys remember that cross multiplication idea, but I'm just trying to get the fractions out. So what I would end up with on the left is n times n squared plus 2n plus 2. And we're trying to determine if that is in fact greater than n plus 1 times n squared plus 1. Now I'm going to need to distribute on the left and FOIL on the right to see if this simplifies. So I'm going to end up with n cubed plus 2n squared plus 2n on the left, and we're trying to see if that's greater than the right-hand side FOILed out, which is n cubed plus n squared plus n plus 1. Now what we need to do is, combine our like terms to kind of move things around. So we're going to minus our n cubed over, that'll cancel on the left, but it also, that'll cancel on the right, but it actually also cancels on the left. We'll minus over the n squared, and we'll minus over the n. So we're just basically cleaning this up and getting all of our terms on one side. Okay, we can also simplify this a little bit. So let me move this up here and then we'll simplify. So 2n squared minus n squared would just be n squared. 2n minus n is just plus n. And we're determining whether this is greater than what's remaining on the right-hand side, which is 1. Now remember, our n values for a sequence, we know that n must be greater than or equal to 1. And because of that being true, even if we're at our lowest value of 1, 1 squared is 1, plus 1 would be 2. So would 2 be greater than 1? And this is when we're at our lowest value of n equals 1. And we know that yes, that is true. So if it's true for our lowest value, and because we're dealing with a positive or a plus n, so n squared is always going to be positive, plus something else is always going to be positive. This is only going to be growing on the left-hand side. Then we know it's true for everything. So in this case, it is true. It is going to be decreasing, and we have in fact proved it. So this statement here is a true statement based on what we know about the n values, that they have to be positive integers. So that kind of wraps up our sequences discussion. We'll talk more about it in class.